into thermal energy capture devices. In turning our attention to thermal energy capture devices, we realized that we needed to redefine the scope of our project and shift from energy conversion to energy capture. Energy conversion can only occur after the energy has been captured, and we believe that we overlooked the difficulty and the nuance of the energy capture within this environment. For these reasons, we designed 3 different systems that we believed would properly capture energy in the playpen, as previously stated. The first design does not require actuation of the doors or the hood. The doors come in contact with the sides of the hot boxes and conduct heat out of the boxes into a working fluid that flows through the doors. The hood is then lowered over the top of the hot box, and a fan pulls air through a heat exchanger in the hood to extract heat in as many different methods as possible.
So the second design we worked on was essentially a cross-flow heat exchanger. So air would be forced through the air outlets up there, and it would potentially be possible to install ducting to reattach those outlets to the inlets, one on each door. And then the doors wrap around the hot box, which is inside, to force air upwards. And essentially it would preheat the air so we wouldn't have to keep drawing in room temperature air. And it would be possible to heat water going through the tube winding in the hood there.
Third design is essentially a 3-sided insulated enclosure system. The idea is that you have a vent system on top that's just a bunch of thin copper strips, and you have TEGs on one side. So the forklift can simply drop the box off inside the enclosure. Then as heat rises to the parts, the insulation helps keep heat from escaping the sides, and then the heat will heat up the copper plates and thus heat up the thermoelectric generators and thus create a voltage difference. For the first design, we did some preliminary engineering analysis. So we did model a thermal circuit, kind of like a 3D thermal circuit, if you will. So we wanted to model the heat transfer to the sidewalls of the heat exchanger, the hood heat exchanger, and also the heat loss to the front. Since there's no heat exchanger attached to the front, we want to determine how much heat are we losing by not having one there. So what we did for the front heat loss term is we just used the thickness of the hot box to determine the conduction loss of the heat through the front. Then for the side heat exchangers, we used that same hot box thickness as one resistor term. Then the next resistor term in series is just using the thickness of the actuation door. And that actuation door is what connects the heat exchanger to the hot box itself to allow that conduction to occur. Then the last set of terms is the heat transfer to the hood of the enclosure system. So since there's no forced convection occurring, it's only natural convection occurring right now. So we used a natural convection resistance term to determine the heat rising from the parts to the hood of the heat exchanger. And then the last term is just the conduction, so just the thickness of that hood to determine the heat transfer to the hood heat exchanger.
For the second design, we did some preliminary heat exchanger analysis, and the biggest approximation that was made here was without using CFD, it's difficult to calculate the convective heat transfer through the parts. So they were approximated with a tube bank of similar properties. And then LMTD and effectiveness NTU methods were used in Excel to generate this table of potential performance using those specified flow rates. And in theory, that could boil water, at least at first, but it does drop off pretty quickly. Yeah, so the design matrix that we looked at for all 3 designs yielded the highest score for the first design because it showed the best balance of all the different types of heat transfer and convenience. And if you look here, next slide, we have the conduction in the doors, the convection out the top, and we have radiation essentially everywhere. There is a good amount of radiation still going on in the playpen, even if you could get more convection if you force the air. The doors operate by pushing the box onto these levers, and then they close automatically, which seems like a convenient option, and that helped persuade us of this design. Some challenges, though, do exist in the fact that the hot boxes don't have straight walls. They're kind of bowed in and bent out of shape. So it would be maximizing the contact to increase the heat transfer. And another challenge would be connecting all the pipes together without restricting the flow of water or the motion of the system because they're generally rigid pipes.
So in the interest of analyzing our design, I ran a transient thermal numeric analysis. in two different stages. In the first stage, I tried simulating the state of the temperature of the hotbox with the parts in it at the time where they leave the forging bay and are ready to enter into the device. And in the second stage, it accepts the results of the first stage of simulation as the initial condition, and it attempts to solve for the temperature inside of the empty heat pipes after the hotbox has been inside for 5 minutes. And I tested different heat pipe materials, steel and copper, with both perfect coincident contact as well as with a 1/10 of an inch gap. And these are the results. And in the future, I would like to further refine this but to optimize for the heat pipe position, geometry, and number, and potentially even estimate volume flow rate of the working fluid.
So next, we're going to get into our plans for the spring semester. We have a Gantt chart here to kind of organize our plan for the spring. Our first phase is we're going to refine our design from this semester. We're going to assign subsystems, each person to kind of oversee the development of. The next phase, we're determining the manufacturing methods that we need to use for custom made components. And then we'll also be determining what components we can just order directly from MasterCard. Then the third phase, we'll actually put our prototype together. And in the last phase, we're going to be doing testing in the MSW materials lab to kind of see if we have a proof of concept and kind of refining our design until we have desirable test results. To conclude, this semester, we're able to define a problem statement based on our customer request. We're also able to define objectives and constraints based on engineering analysis and input from our customer. We're able to research different types of heat to electricity conversion methods. We're also able to determine the optimal location of the playpen by doing appropriate engineering analysis. Additionally, we're able to determine an energy capture device concept using appropriate calculations in our background research. And the spring semester will focus on refining our design, doing some prototyping, and doing some testing in the MSW materials lab.
Any questions?
Perfect.
I have one, and maybe this is just my misunderstanding of how this process is gonna work. Forklift takes the box of parts, puts it in a chamber, right?
Yes.
So you said that as the box is going in, there's something that's gonna close the doors. How's it gonna close the doors with the forklift?
So
in the
there will
way?
be levers at the rear in contact with the hot box as it gets pushed in, and the force of the forklift pushing in will close the doors.
Right, but isn't the forklift gonna be in the way of the doors closing?
No, because
So
there's no
front door here.
Oh, there's no front door.
Yeah,
Okay,
so-
okay. Like,
No worries,
thank
I'll
you,
explain that.
thank you.
There's locating tabs on both sides to square the hot box as it
Okay.
enters into the location, and then it will press on here. When it is removed, there's gonna be a spring connection between the door and the frame that will reopen.
Thank you.
There could potentially be some some simple human intervention for getting the hood down and stuff, but the idea is that it would help to automatically have some of the process take place.
The lever doors work on both the hood and the.
Okay.
Thank you.
Quick question.
Yes.
So when you're talking about the thermodynamic panel or whatever that little thing was, you said one side needs to be cool, right?
Right.
What defines cool? How much of a temperature difference do you need?
As much as you really can, at least room temperature would be good, but lower,
I'm thinking in July now, it's
Right.
hanging out there. and it's
Yeah.
100 degrees.
in the
outside.
winter it
Is
would
that
be
enough?
easier.
So almost all designs with TGs would have to be actively cooled,
Right.
which is
Oh, okay.
the difficulty of implementation along with the cost.
Okay, because that's gonna offset some of the.
So there's a furnace water cooling system, water would probably be sufficient.
Maybe you did mention, but I didn't hear what you do with the heat that you capture in here. Are you gonna heat some homes around in the neighborhood? Are you gonna heat the company? Or what are you gonna do?
So the ultimate goal of the project is to just capture the energy and generate some electricity. Actually putting that electricity back out into the grid, which is the ultimate goal, is another project. We don't have time to cover all of that.
If I can add to that, part of it was also because they wanted to use that energy that we captured to power these induction heaters that are causing the electric bills to be very expensive.
Can I ask a question?
Of course.
Does anybody think that from a sheer physics standpoint, is there anything, does anyone see anything obvious that was missed? Because it's an interesting problem, and there's a lot of different ways to recapture that. The amount of BTUs is incredible. So from a physics one standpoint, just bare physics, does anybody see anything obvious? You know, sometimes there's a 900-pound gorilla, and I think we got a room full of really smart people here. Anybody see anything that was like glaringly missed?
I mean, I have a little forging background. I worked at Scout Forge for a while, and I guess my big glaring is that no one else is doing it, which means that it's probably really hard to do.
Right.
I mean, you're trying to turn thermal energy into electric energy, which is super inefficient, no matter what way you do it.
So it's going to Mars, but we're doing it. Anybody see anything we're missing?
Obvious to me.
All I know that bill that we pay $36,000 a month, that can heat was 72,000 homes.
I'm to be blunt, I'm a capitalist, so I'm more interested in reducing the $35,000 rather than heating my neighbor's house.
Yeah.
We probably pay more for, so our facility is about 40,000 square feet. Think about that for a second. Now, a lot of companies in this state pay more for electricity, Harley Davidson, Modine, for
Way bigger.
40,000 square foot facility. I'm not trying to say.
We'll get there one day.
Sure.
You guys look at, if instead of picking up on the forklift and then putting it in this, have you thought about slowing down the process with the line where you can capture this as soon as it gets out of the oven? Because your highest thermal degradation is as soon as you leave.
Yeah, no, most definitely. The issue is that the amount of mass that has to be moved with each forging stroke causes residual stresses that increase as you decrease the temperature of the material. And so if you forge at the highest temperature possible, you'll get the best quality parts. And so as soon as you try and extract any energy from the extremely hot parts, you're compromising your product.
And if I could add, even if you're just intercepting it at that point, the way the conveyor belt works is there's really only one part at a time and it gets taken away pretty much right away. So there's high temperature, but it's low average because there's not always a part there.
It's just like a spike,
Yeah, it's very hot for
Yep.
a minute
femtosecond, yeah.
versus we have, I think we did the calculation, it was like over 1 million BTUs of energy just sitting in the boxes as they're cooling. It's good. Yeah, so,
Yeah, better place to go after.
yeah.
Yeah.
Yeah. Any final questions?
In terms of your secondary fluids, do you have an idea of what temperatures you should be looking for to ultimately lead to a power or thermal to power
Yeah, so
version?
ideally, we would like as big of a temperature difference as possible. The power generation method that we select is going to be the driver. If we're going to be focusing on Stirling, we're going to have a really low thermal capacity fluids. We can jack up the temperature as much as possible. The parts in the playpen, it depends on what point you get there, but you can get temperatures as high as 800, 900 degrees in the fluids, which would be enough to drive energy production in even something like a Stirling engine. But most other temperatures, we're going to be seeing 100 to 200 degrees Celsius, which should be enough for some low-end organic Rankine cycle use. We found literature that stated that there were organic Rankine cycles that were used as low as 70 degrees Celsius on the hot side and as high as 35 degrees Celsius on the cold side.
All right, any other questions? All right, thanks, you guys.
If you guys have any questions or talk to the clients at all, I guess, if you want to do that right now, you guys can Head out, but I have to do one more presentation before. So. I've done so yeah.
Great job. Thank you.
You wanted a picture, right? I can get that. You wanna get some pictures?
Oh, yeah.
Sorry to disrupt.
Yeah, I think I'm gonna get that.
Nice.
I've already. Like leaving? Oh, they're gonna go. Sorry, quickly over picture. That's okay. They're gonna go meet with the clients.
What's that?
The
Yeah.
last group was gonna talk to the client after. Rather than disrupt us.
Oh, that's terrific. All right, everybody's clear?
I think everyone is clear. Ooh. So we have to delay the
Yeah.
build suspense.
Yeah, no, it's great, right on time. When you're ready.
Good afternoon, advisors. Good afternoon, students. We are the American Society of Mechanical Engineers Student Design Competition Team for MSOE for 2025. My name is Matthew Zupan, and I'm Tim Schultz, Tony Beekle, I'm Luke Anderson, and this is our senior design presentation for this semester. So what we're going to be going over today, most importantly, for at the back, going over our problem statement, touching on some different project requirements, different background going into that. Before then, we can actually jump into then our design and some decision-making processes that we've gone through so far. After we've kind of gone through all the background stuff, then we can jump into our subsystems, kind of how we're breaking down the solution to our problem with those different subcomponents, and then move into our future progress as we go into semester 2.
Yeah, so starting with our problem statement, we were given all the rule sets by ASME directly. Looking over those, we were to accomplish the tasks that were given for this year as the competition changes yearly. What we were tasked with doing this year was designing and fabricating a robotic vehicle that is able to maneuver around a box city landscape at scale, be able to pick up bins that hold cubes that are either garbage and recycling, intake those into the robot where they are then going to be sorted into their individual types. Those are then going to be distributed into different bins for deposit, again, going into kind of the whole fundamental process of environmental and trash cleanup as a whole. We further specified what our team wanted to accomplish through these design parameters and came up with the following. Our robot has to fit within the following requirements of 4 inches by 5.5 by 12. Reason for this being that the actual competition itself has some design limitations. The main one being the minimum width of the lane is about 10 centimeters, or again, about that 4 inches in width. We also have to deal with overhangs over top of the road that are about 6 inches from the position of the ground. We also need to design a robot that is able to follow standard law traffic and also avoid any obstacles or deal with them as seen fit, such as potholes or hills. Further, we decided to have our own requirements for the team to make sure that we actually pushed ourselves and we're actually designing something that was useful, not only for the scale of a small robot. We wanted to automate our sorting process so that we didn't have to manually choose which cube went onto what side for deposit. We wanted to be smaller than the road, obviously, but we're going to minimize that as much as possible. And Matt will get into this in a bit, but we're going to have only one rotational port for our collection on the front where our arm mechanism is going to be. If we have further time, we are also going to look into automating our dump and grabbing mechanisms as a whole. So one of the few things that we started to look at was actually what we were given for our schematic for what our field can look like. We have in green all the different bins that are going to be holding all of our cubes, the way that we can travel around the road, potential dump sites, the receptacles we're putting things in, buildings that can get in the way. There are a lot of factors to take into play when designing the robot for this, which is why we then started going into our decision-making criteria for this. 8 of them are listed up here. These were the primary ones that we used, mainly because these dealt with majority of the design as well as competition aspects for the robot. Our weighting is off onto the right. This presentation will not actually go over majority of how our designs got there for sake of brevity on time. Otherwise, we would be here all day going through each decision matrix. So without further ado, I'm going to transition it to Matt to start talking about our subsystems.
All right, thank you, Tony. So we're now going to jump into, like you said, all the different subsystems that we broke down to the actual solution of our project. We're broken down in a very modular sense so that we can kind of look at stuff piece by piece throughout the collection to dumping of all our bins. So the first one that we're going to go over is the arm/grabber. The goal for this one is to be going around and actually grabbing the bins that are on the playing field. There's 4 big requirements that we kind of set in stone for this actual system. One being that it's folding into the space limitations. The main part being the static height of the 5.5 inches that we're working with, as that's kind of the height of the different overhangs that we might see on the roads. The second one being that we are going to be having to grab boxes on both the left and the right side. So having that 180 degrees of sweeping grab is kind of how we're going about doing that rather than having 2 arm systems. The third one is into flexibility. This is a big piece as we're grabbing stuff at different angles, we're grabbing stuff at different distances. There isn't direct output from the actual competition of what that distance might be, but we're expecting somewhere between 5 centimeters to up to 12.5 centimeters. Along with that, then we also have stuff that we have to account for in the gripper, being that the collection bins that we're grabbing are somewhere between 1.5 inches and 2 inches, kind of in that variability range there. We also have then the potential that they were grabbing between buildings, so being able to fit between that is also another constraint. So with that, we're now going to jump into kind of 3 different concepts that we have for the arm, and then get into concepts for the grabber after. This first one was the first idea that kind of came up with, very similar to a CARES design for automated side loaders that you see in garbage trucks in the actual real world. Biggest one with this is that they've had a problem that there's very little range of motion that we're using, so this one was scrapped very early. The second concept that we're going into, and it's actually pretty similar to the third concept, and these are both kind of different arm systems that we're using instead. Biggest thing with these is that they have full axis motion, which let us kind of get away with the different variabilities that we're seeing. But the difference between the second and the second one here is its biggest thing is that's using a linear servo for that range of different distance range that we're grabbing at. The problem with the linear servo that we were seeing is that for the further distance, the further variability and range that we're trying to do, the larger, the heavier, the more expensive the servo is getting. They're also pretty slow. Being able to get up to that range distance that we're looking at was going to end up having a cost of up to like $200 for a proper good linear servo, which we were like, that's not very feasible for our project. And being able to build one out of a rotational servo was increasing size, which we are very limited. So that left us with our third concept, moving away from the linear servo and instead moving towards more of a pivot rotational servo being used for our variability, as that rotation is then being used to be able to grab at different ranges. This then led us to our actual SolidWorks model after different kind of 3D printing concepts and moving on to different stuff. This is what we ended up with, being able to reduce size as much as possible, while also be able to get all the different requirements that we were trying to do. So with that, the biggest thing that we wanted to hit, being that we're limited in size, we're trying to reduce weight, we're trying to reduce all those different pieces based off of kind of like how our decision matrix was earlier. You can kind of see on here that there's different parts of the rotation that are experiencing different torques. Being able to minimize the size of the servo, because the larger the servo, the more torque it's going to be outputting. Be able to minimize those different pieces is kind of the biggest goal with this. So you can see on the kind of, if you go back on the left part, where we have the more pivot servo at the base, that's going to be experiencing the most torque, calculated that to be about 3.27 pound-inch, where then something more like the pivot is going to be experiencing less. So then with that, we can move into the different components, being able to minimize of the kind of like factor of safety with that stuff. If we don't need the servo to output as much torque, we can get away with the smaller one. So now with that, we can kind of jump into the actual like gripping mechanisms. This first one was kind of the first one we came up with. It's kind of like a clamping mechanism. Biggest problem with this one, the reason that we didn't use concept 1 and 3 was the fact that we had to go over the top of the box. This is very difficult for the user to do, as they're all manually positioning that, being able to go down on top of it, especially with the kind of servos that we were working with, was not going to be easy. So this left with our second design, which was more of like a pinch design. This is using a 4-bar linkage and different gear systems to move together to be able to have a parallel motion in our grabbing. It's really good for having to be able to grab at different angles, Also be able to grab the boxes between buildings, which was kind of one of our requirements. This is kind of the concept 3 that we had, like I said, had to come down the top good. So this is kind of what we're working with so far in terms of the grabber design. We're moving more into semester 2 for this, as we were focusing more on the arm and different components. But we had like base models for the different sizes that we're working with to make sure that the 4-bar linkages were going to get the variability and grip widths that we were working with.
Right, so after the bins have been dumped into the robot, the cubes inside those bins need to be sorted. You need to be able to take those cubes from any size of 0.5 to 1 inch. And because there's a variation in those sizes, you will have anywhere from like 3 to maybe 90 cubes entering the robot at any time. So you need to be able to design a system that can take any sort of inflow like that and then sort them based off of color. So the main challenges that this faced was the movement. How do you get these cubes all in the same spot so you can take a look at them and then sort them based off color? How do you move these cubes out of that sorting position without dragging any other cubes into wherever you want to put them? And then also just the size and scale of this. When a cube is at a 45-degree angle, so it's sideways, it's about a bit more than a third of the size of our robot. So there's a lot of space that's taken up inside the robot by this sorting system. So what we have right now, which I'll show after going through the design process, is a gravity-fed movement to a single position based off of vibration. The cubes are indexed based off a specific geometry of the sorting hands. And then we move the cubes vertically at the end of the sorting system to reduce the impact that the size of the cubes has. This is the first design. It's quickly moved off of because we gained more information about the competition from a rules update, but it's a good first look at what's happening inside the sorting system. So this section vibrates and causes the cubes to move downwards towards the sorting system. This design had issues where they would fall off, and twisting cubes doesn't work super well, so this was quickly scrapped. But on the second design, we have a profit base now, and you can start seeing the geometry that we're using to push the cubes off. Sorting arms aren't in this one, but you can see the outline of that they would have. This one also adds walls so that the cubes are more stably inside and a profit base so we can test it out. Here's the third one. This is what we have right now. It has the sorting arms in there. You can also see that we have not just our springs and stuff so that we can start looking at how this is actuated in the future. And this sensor will go here and the cubes will end up here, be sensed, and then push off to one side or another and then fall out the front or back, depending on how you look at it. So the main issues that we have right now are these parts are relatively complex for 3D prints. So this has caused issues with 3D printing where we've had layer delamination and just failures overall. So to improve this, the parts will need to be improved so they are less complex. These are the components we're using right now in the sorting system. This right here is the vibration motor. This is the servo. We are standardizing servos across all components of the robot. So we've got two separate servos. We're using a small one and a large one. The sorting system only needs a small one to actuate the sorting motion. And right here, we've got a color sensor, which will be used to sense the color of the cubes. This is the basic electrical layout of the robot. So we have to battery power the robot. That's in the competition rules. And most of our components require 5 volts. So the main control board requires 5 volts, and motors and servos are rated from anywhere from 5 to 6 volts. So we've decided to use a 5-volt power converter that we found in AdFruit that's able to take a variable voltage input and output a steady 5 volts, and then power everything off of that. We were planning on using an ESP32 to control the robot. It will host a web server and also its own local Wi-Fi network. So we can connect to that using our phones and then control the ESP using our phones at the competition.
So the lock mechanism, so now we've sorted all our cubes, we need to actually get the cubes into the receptacle and get going. So to do that, we need some sort of mechanism to lift that with our basket that we have, or bucket, I believe we call it, in order to get them into the receptacle. Also, The cubes also must be moved control. The cubes must be dumped controllably enough so that they don't spill out of the receptacle when they're dumping, so they don't hit the front of the receptacle or the back of it. And something we learned that during our conceptualization phase is that receptacle is almost as high as a robot, so we have to lift our bucket up high enough to where the exit point is at just over 4 inches. So here are our initial concepts. You can see that we haven't fully taken that third point into account yet. We have our output link as the bucket. The business design is based on an actual garbage truck mechanism with the linear actuator replaced with essentially a 2 forward linkages in one. And the second design was more experimental. It was a spring loaded. We spring load our bucket and attach it to a wire in which that rotates. It's either up or down. Obviously, that design was not good because there's a lot of force at play and it potentially fail, and the stresses. And so our current concept is actually a 6-part mechanism. It, as the name implies, it stretches to allow the output link to raise up and also turn, which fulfills our dumping, which satisfies our targets for like our dumping in motion. So then we made it in SolidWorks. These are like the initial dimensions of the links. These were just to get a feel for like how it would be sized, how it would like it would be a lot of space that is given, which is about 6 inches. The bucket design was also just to get a feel of how much space we would have for cubes. And the second design, if we it has a more fleshed out version with a smaller linkage, 20% reduction. So, and the bigger part is the fleshed out bucket design. So you can see there's now 2 sections for sorting cubes. And in order to solve the height problem for good, we use ramps to elevate our exit height for the cube so that we can clear the 4-inch space you can dump in receptacle. And during our so we built a prototype of the second design, and what we found is that at the linkage works best when we push the basket up directly. So we've made a cam system and we polarized pushing arm that will essentially operate the linkage indirectly, while the linkage is able to guide the motion of the basket. We also move the linkage to the side to allow space for a servo motor, so that it can actually move the arm. And I'm currently working on prototyping this. It's not finished, but I will have this finished next semester. In order to make sure that this will work, first I did a simple torque calculation, force equals force times length. So the force was the weight of the bucket, which the model was ABS plastic, and based on the sulfur evaluations, this was the weight of the bucket. The effective arm length of 3 inches comes from the point of contact to the center of the hole in which the servo motor resides. The required torque is calculated from that. This which is sufficiently below maximum motor torque, which should operate fine.
Yeah, so I'll take it from here. We have all the rest of our subsystems ready to go. The next thing that we're going to try to accomplish are our motors and our drive base that is going to hold all these components together. Roughly on this screen here, I have all the conversions that were given for the amount of force that we were given for the motors because we needed rated and stall torque, converted those to angular velocities, computed those into power capacities. What we started with were actually some 6-volt N20 motors that were donated or given to us by the Midnight Robotics team here on campus. Given some reference tables, we were able to do some rough calculations and get a value of 0.079 watts per motor. Doing some initial calculations on the amount of weight and amount of torque that we needed wasn't going to be enough, so we decided to bump up our size to N30 motors. There's a significant increase already, if you guys can see on this page, but the big thing was that the power output or torque was about 10 times that of the original motors that were chosen. Speed is significantly reduced. Again, those N30s have a 1 to 240 gear ratio reduction. However, we can always gear those up to speed them up if deemed necessary. Overall, though, the M30s were chosen because they had sufficient enough torque and can be sped up if needed. Lastly, our drive base, which kind of gets into how everything's coming together, holding all the different mechanisms. It's pretty rudimentary, but it needed to follow a couple things, needed to make sure it was able to hold all the assemblies properly, easy access to everything that was on there for implementation or fixing, needed to be lightweight, but also not bend under the weight of everything that was in there, which kind of eliminated our 3D print idea for having the drive base. Walls are put in there in place so that you can kind of see where everything's supposed to go. Platforms right there in the front so you can actually see where the arm's supposed to go. Moving into our second design where we improved on a lot of things, you can see a lot more access to components. There's expansions that were made, but our biggest issue was still height. Looking at all the components that we already had, the biggest issue was that our 5.5 inches was being exceeded with the total amount of components that were on there, primarily from the arm mechanism and the sorting mechanism. So our current design, which looks at a lot of these, is actually factoring for this by having some channeling in the back, as well as a platform in the front that has a section removed so that a servo motor can sit in there, and for the back by the dump, the linkage can actually sit into the robot itself, reducing its overall height. Overall, this is the one that we're sitting on. It takes into account where the wheels are going to be, the motors, as well as all the different electronics that are going to be on there. What needs to get done for this is just make sure it's assembled, making it out of aluminum stock right now, 0.1 inch or about 10, 1/10 inch, thank you, 10 gauge. 10 gauge, thank you, yes, 10 gauge stock. As it sits, our current assembly looks something similar to this, where in orange we have our arm mechanism, in green we have our sorting mechanism, back in blue our dumping mechanism, all held on top of our drive base with our electronics sitting in that platform, the batteries denoted by yellow in there. With our full assembly made, we wanted to tackle the next thing, which was our budget and future planning. Currently, we have our budget to be around $500 to $600. Currently, as everything stands, purchase components and components that are needed to be purchased, we're sitting around $330, significantly under our cost of production alone. This doesn't take into account any of the traveling costs for competition because we'll be going down to Florida for that. But as the robot itself stands, this is our total cost. To conclude with our future progress, we still need to make sure everything is fabricated and testing everything on the 3D prints. We need to machine and assemble our drive base. We're working on finalizing our electronics where they're sitting and how they're hooking up to everything. We're going to start work on controls and coding, and then as any good team should, we're going to keep iterating on our current designs until we get a robot that is efficient and effective at what it's doing. So with that, we are out of time. So thank you for listening. We're opening the floor to questions. Okay.
How does the sorting actually take place? Is it automatic or manual?
So yeah, sorry, it's automatic. There's a sensor. It reads when there's a cube in place. It reads the color of the cube. Then it actuates. The actuation of the sorting system has not been fully developed yet. There have been some preliminary looks at what we're doing. They'll try and move it up to the left or right, and then it'll fall out of the sorting mechanism into the dumping section.
Yep.
First.
Are you having any issues with the arm gripping the cubes or any profile on that?
Yeah, so the biggest thing is that we're gonna be grabbing at different like angles and stuff like that. So obviously you have to think about it if we're grabbing the box and it's like this, being able to do that with the gripper is kind of like the biggest deal. Because like at first you might be like, okay, well you could just put like rubber or some sort of like sticky kind of thing to let you grip onto it. But then the more you do that, the less you can rotate the box depending on how you grab it. So you want more force to be able to grab it by the actual like plates coming together to grip it, which is why we wanted to go with something that kind of allows it to have that parallel motion so that it can grip it depending on like the different variability, while it's then still being able to reorient the box by it slipping on the actual like arms rather than getting away with trying to use rubber or something like that.
Do you have an idea of how much pressure you're gonna have to exert on the box in order, they don't weigh much, but how much pressure you're gonna have to exert in order to pick it up and keep it from sliding out of the jaws?
We'll have to do more like friction analysis on that. The only problem is that from the competition, we don't necessarily know the exact material that we're expecting to see. The rules like do not, it says it is some material that is decided by them. Like, okay, fantastic. So being able to do different testings with like PLA and stuff like that should be done once the gripper is actually like formulated. But I mean, the servo itself is able to put out that 2.17 pound force inch. Since those like linkages are only an inch in general, it should be able to have enough force applied on the box that it shouldn't matter if it is like plastic to plastic or something like that. But we'll have to kind of see in testing how that actually works.
Thank you.
Was there another question?
I was just like ask like, are you guys using a controller to just drive this around and?
We're flying and using a phone.
Okay.
Yeah.
So it's all like operated through a phone, you'll
Yeah,
be
yeah.
intentionally grabbing it and then picking it up and then.
Reason for that being, what we didn't specify here is that there is also a competition box that we have to fit all of our components and tools within. That would include a controller. So to minimize on that size, we're using a cell phone instead. Because again, what's not listed here, the box size does actually attribute to our score. Because this is a competition, there is a score. So we're going to need to address that problem by making the box as small as possible. Yes, Toby.
2 questions. Who's your pilot?
Unknown.
Unknown currently. I do have a little bit of experience from Vex Robotics maneuvering a robot around. So, and I know Luke, you also do Midnight Robotics.
Yeah.
So we do have some potential experience on the team.
Does the cost of the phone also contribute to your budget then?
No. That is assumed to be anyone could almost download the application that we're going to be using and be able to control the robot themselves if they have the app.
And to add to that, we're also trying to figure out whether we have to actually put the phone in the box.
In the recent Q&A, that was teamed, yes.
Yes.
We get Q&As throughout the year when people ask questions and they answer them. So this one was determined was it Tuesday?
Yeah, it's like a week ago.
You're gonna be turning some really sharp corners and all of those things.
Yes.
How is your steering system, whatever?
So our steering is actually done by all-wheel drive. So what I've gained from a lot of like robotics competitions in the past is having all the motors be driven by, having all the wheels be driven by motors independently means that you don't necessarily have to have all the steering mechanisms on the bottom. All you have to do is say, I want this motor to turn this much, the other motor to turn.
So skid steer.
A little bit of skid steer. Again, it's typically called as all-wheel drive. We went through a lot of iterations on doing FWD, back-wheel drive, making sure that we have all of them kind of put into place. But that's also why in the front, I actually have some notches turned out so we can actually maneuver around some of those corners a little bit easier. Because again, if we're trying to just put a box on a road, it's not going to hit the corner very well. That's why a lot of cars don't have just boxes.
And also to add to that, we have omni wheels, so you can easily skid steer instead of having to deal with wheel friction. The wheels have little wheels on them so that they're able to slide easily.
Okay, I want to get to your question, then we'll get to the two in the back.
Yeah, so you said everything has to be controlled through a battery. Have you tested to see if, dare I say, running all the motors, how many motors can you run at the same time? Are you limited in, I hate to say, power and ultimately energy to make your complete lap? How many stops do you need to make? Is there an optimal, I hate to say optimal pattern, but have you figured out like a pattern? Are you gonna have to make multiple trips, et cetera? Is that?
Yeah. Okay, so
been addressed?
We don't know the competition layout yet. That what was up there was just an example, and that was only for the preliminary driving we have to do. There are 2 sets of driving you have to do. You have to do a preliminary where you don't even have to sort the components, and then you do a head-to-head competition where 2 bots are under a large play field. They go against each other. We know how much power the converter is capable of putting out. We don't know numbers on power draw yet. That requires us to know how much weight we're going to have on board, and we still haven't completely finished our design of components.
Plus, we first only got our motors and servos in not that long ago.
Yeah, so more testing needs to be done so that we know how much power draw we're gonna be taking.
To answer the second half of your question, we are gonna have to plan out our routes while we're there at the competition. Because currently where it stands, we did optimize the dump mechanism to only intake a certain amount of cubes, which might not be indicative of the total amount of cubes on the play field. So we are going to probably have to do several trips. I think the first initial play test can be about 5 minutes and that competition can be about 10 minutes long. So we are gonna have to factor that in. That's why we did choose the 12-volt battery to start. Because the higher we have there, the more we can keep running everything. And again, everything here is such small scale that it should be able to run pretty good. We're still gonna do calculations on it, but all in all, should still be able to run pretty efficiently.
So do you expect to, like, it gets developed, do you expect to run out of power, or do you expect it to be kind of close? Is that like a hard, I guess the question is that like a really hard constraint, or is that like a?
It's not a terribly hard constraint for us right now. If we do testing and see that it is going to be more of a hard constraint, then yes, we will take that into account. The biggest issue is that we can only have one robot and only one battery on that robot. So we would need to, I believe so, correct?
You can change the batteries.
Well, you can change them between competitions. However, while it's running on the field, you cannot change the battery. So that one battery needs to power it for that entire competition run, so to speak. There were 2 questions in the back. We'll try to hit them real quick, but unless we are gonna have time. I know we're running.
We're at 30, but you can take another question or two if you want.
I had curiosity, if you're using Omni wheels, are each of the motors going to be like diagonally driven, or is it just like on the shaft and you're gonna?
On the shaft, correct. Direct motor to wheel output.
It's 2 Omnis and 2 regular wheels, just.
Oh, okay. So
yeah, traction wheels in the front, Omnis in the back, so that we can actually get some sliding motion.
Oh, that's.
Any other questions?
All right, thank you. That concludes the session.
Okay.
What?